Okay, yes, thanks very much. And I'm very glad to be here. And actually, this is the second time in CWI. Okay, today I will introduce a paper with Ashley Montanaro. It's about quantum and classical complexities of computing functions of matrices. And yeah, this is the outline of the talk. First I will introduce some background and motivations. Then in the second part, I will introduce our main results mainly about the law bounds of this problem. And the third part is about the BQP completeness of this problem. And finally, I conclude. Okay, I will start from quantum linear algebra because this problem is mainly a linear algebra problem. We compute functions of matrices. Quantum linear algebra is actually it's a very important. It plays a very important role in the development of quantum algorithms, and we can find the quantum advantages in this area. I guess the first problem is Hamiltonian simulation. Of course, the background of this problem maybe comes from quantum physics, but just look at the datum of this problem. We just computing e to the IAT and a quantum state B. So here A is a Hermitian matrix, and I is the imaginary unit. So we just compute e to the IAT comes a vector, a quantum state. And this is a fundamentally important problem in quantum computing. And another problem is solving linear system problem. The first algorithm was given by Harry Haskin and Lawyer in 2008. In this problem, we are computing an inverse times. And linear system is a quite important problem especially, for example, in machine learning. And this algorithm greatly promoted the development of quantum linear algebra. A main reason for this, I guess, because it has many applications, for example, in quantum recommendation system problem and solving differential equations. In the quantum recommendation system problem, we are computing this greater than dagger applied. It is applied to cat I is the ith column of this matrix. Here A greater than dagger, it means that we do the truncation. We only care about the singular values larger than some data. And solving linear system differential equations is a problem we just compute into the exponential of function of AT. Here here we don't have the imaginary unit here. Okay, these are some examples of the applications of solving linear system problem. And as you can see, all these problems can be described as computing functions of some matrices. If A is applied to cat B. And generally, this problem for any function f and matrix A, if you want to compute fa times b, and there are some techniques you can use in the quantum case, and I guess maybe the most simple one is by idea similar to the HHL algorithm. You can just design a quantum algorithm to compute this quantum state. But maybe more recently, there are some more advanced techniques like quantum singular value transformation. This is a more efficient algorithm to do this kind of task. So in the following, I will focus on this quantum singular value transform. It is called QSVT. Here I will state a simple version of this QSVT. I assume A is a Hermitian just for simplicity. And I also assume A is bounded. The operator is bounded by 1. So what QSVT does is the following. We are giving a unitary U such that the top left corner is this matrix A. And F is a bounded polynomial of degree D. Then from QSVT, you will find a quantum circuit, a new quantum circuit, such that it a new circuit U theta such that its top left corner is FA. And here, more important thing is this new circuit, it uses this U and U dagger, and also including their control forms, order D times. So here, D is the degree of this polynomial. So as you can see, this kind of new circuit is totally determined by the degree of this polynomial. Yeah, this is basically, what QSVT does. Of course, QSVT can do more, not just for Hermitian, but for Hermitian matrices, it's easy to state. Okay, so as a direct result, when you have U theta, you can just apply U theta to a state you care about, and you will obtain this state FA times B. Okay.
What exactly do you mean by computing FA of B? Do you want to produce a quantum state?
Yeah.
Otherwise, do you want to get the amplitude?
Yeah, generally, what I mean is just prepare a quantum state of FA times B. Yeah.
It could be that FA really shrinks things,
Yeah,
right?
that's
And then you
possible.
have to apply amplitude
Yeah,
amplification.
that's right. But what I mean is that this gives a method to do this to solve this task.
Part of the method.
Yeah, of course.
And the one bounded means it's at most one always?
One bounded. Okay, here I mean fx is smaller than 1 for all x in an interval. Okay, that's a good point. Here, by computing FA times B, I will explain a more specific problem later. Okay. Yeah. Of course, if f is not a polynomial, you can just find a polynomial approximation of this function and using the same trick. Okay, so this is the motivation of this talk. For functions of matrices, as it's quite fundamental in quantum computing, and from the known examples, just for example, the examples I mentioned in the beginning, if you apply QSVT to prepare the quantum state of FA times B, usually the quantum algorithm based on QSVT is optimal. And of course, it's quite interesting to ask, what if there is any result about this optimality, maybe in the general case. And another interesting question in the quantum case, we want to know, the classical or quantum classical separation for computing functions of matrices.
But these, the classical problem, like what is the classical problem? Because if the quantum problem is to apply the matrix instead, the matrix function is to...
Yeah, I guess, okay, I will explain this. So classically, in the quantum case, usually, for example, FA times B, usually we obtain a quantum state of this, this new vector. But in the classical case, usually, the algorithm sometimes return a vector of this thing. So as you can see, quantumly, it's quantum state. Classically, it's a vector. So it's something.
Oh, you mean it's like a vector with all the entries?
Yeah. So you see, they're quite different, right?
No problem.
Yeah. So sometimes when we compare, when we say, okay, there is a quantum speed up, sometimes it's maybe not a nice way to say we have some speed ups. So in order to better understand the quantum speed ups, we consider this kind of weaker problem. We don't consider a quantum state. Instead, we just try to compute the entry of this FA. So the problem is defined as f is a bounded function from -1, to -1, and we assume A is a sparse matrix, and also it is a Hermitian. And its operator is bounded by 1. Yeah, here we care about the the task is just to try to compute the entry of this FA. So you see, in this case, FA, the IGS entry of FA is just a number. So you can design quantum and a classical algorithm to compute this quantity. And in this case, maybe the comparison is more reasonable because the task is similar. You have the same input and you have the same output. up to some accuracy upscore. The definition of A is where we use eigenvalue decomposition. If A has an eigenvalue decomposition, then FA is applied to the eigenvalues. Here sparse means the number of non-zero entries in each row and column at most case. Yeah, here, okay, I have to say the reason we consider sparse matrices is because when we apply QSVT, for example, when we apply QSVT, we start from this unitary U, the top left column is A. But usually, if we are just given A, how can you find this kind of unitary, right? And a simple case is that, if you know this matrix A is sparse, then you can efficiently construct this U. So that's the reason. So here we only consider sparse matrices, so that we can apply QSVT.
You need to say U or U tilde?
U. Now this in QSVT you start from U. You assume you have this U, but in the problem you just have A. So how can you find this U, right? So you have to find a way to construct this U efficiently. And if A is sparse, then you can find an efficient way to construct this unitary U. Okay, this is the reason why I assume A is sparse.
But what if, so that you have this matrix A and you need U because A might not be unitary.
Yeah.
It says operator norm at most one. Right?
Yeah, it's just
Possible that you
operator
can't
norm.
implement it. But then, because it has operator norm at most one, that means that it's a convex combination of unitary matrices. So what if can you alternatively think about A's that are sparse convex combination of unitary matrices, and then you can implement A probabilistically by sampling it.
Yeah, that's another. Yeah, that's also another study. Sometimes people assume A has is a linear combination of some unitaries. Yeah, that's also possible. So yeah, if you have that, you can also use it. That's right. And here, we can only consider this case A is sparse. I think there is another paper that considers two cases. One is sparse, and another is just like what you mentioned. It assumes A is a linear combination in Pauli matrices, and they also studied the quantum advantage of that kind of in that case. So in this talk, I assume I just consider sparse matrices.
How is A given to you?
Okay, yeah, okay, well, here. Yeah, so we care about the complexity. So what is the complexity? And we assume we are given two arcross. And I think these two arcross are commonly used in the quantum case. The first arcross, since it's sparse, we hope we know the structure of this sparsity. So the first arc O1, if you are given ij, it will tell you the jth non-zero entry in the ith row. The second oracle just tells you the ijth entry of this matrix. So we assume we are given these two oracles to access the matrix A. And of course, in the quantum case, we can assume we can use these oracles in superposition. And the complexity, query complexity is the minimum number of the cost to these oracles to solve the problem you care about. So this is the query complexity we consider in this talk.
So how do you use these oracles? First, you query the first oracle, and then you want to know the
yes, how to use
the P, or that you want to know the
yeah, I guess here we assume we have these two oracles. You can use these oracles in any way you want. Yeah, usually these two oracles can be used to construct this unitary U such that the top left column is the matrix A. Using some, we can use it in some way. Okay, this is the assumption. That's the assumption. Okay, now next I will talk about the main results. Okay, maybe we can start from a simple example first, the matrix powers. Yeah, this is a very simple example. So we assume A is sparse, then just use the definition, you can compute, m's power of A as the IGS entry, just use the definition. Yeah, because, A is sparse, so each summation contains at most S terms. And so there are, okay, so yeah, there are M, okay, sorry, there should not be, should be M. So there are N minus 1 summations here. So in total, there are just S to the N minus 1 terms in this summation because of the sparse. So just use the definition, you can find a method to compute this entry. Of course, you can use some other techniques like random walks to obtain some, maybe sometimes more efficient method, classical algorithm to compute this quantity.
By the complexity, you mean the number of calls to the previous network.
Yeah, so you see, if you just use this definition, so you need to know all these entries. So you need to use Oracle, maybe at most S to the N minus 1 times. Yeah, interesting thing is for monomial, you can find a polynomial that approximates this monomial. And the degree is square root of n. This definition gives you exact calculation with no errors. But sometimes in this talk, yeah, it's fine to have some errors. Once you know how to compute the IGS entry of a monomial, then you can use the same trick to compute the IGS entry of a polynomial. So the interesting part of this point is the degree of this polynomial is square root of n. So you see, you in total the complexity can be reduced to S to the square root of n. Right? And another point is it was proved that this problem is BQP-complete. Of course, BQP-complete. Yeah, I will come back to this definition later, but BQP-complete basically means, okay, first it is BQP, so it can be solved efficiently by quantum computer. And the complete means any other BQP problems can be reduced to this problem. So it is the hardest problem in BQP. So if we believe quantum computers are more powerful than classical computers, so this problem should be hard for classical computers. Okay, I guess the question is how hard it is. And this is our law bound. This is the current complexity law bound. It is, this law bound tells you it is exponential in the square root of m. Yeah, so if we just look at the dependence on m, so you will see the dependence on m, square root of m is at least exponential. So this is exponentially hard for classical computers.
So if you want to say that this problem is BQP-complete, you have to give an actual input, right? You cannot no longer assume that you have these sparse oracles. So how do you instantiate the problem so that it actually can be a member of a constant BQP? BQP is not about query complexity problems.
Yeah, that's true. Yeah, that's true. And in that case, yeah, we don't use oracles. Yeah, you're right. In the definition of BQP, it's not our. So this is, I guess, this third statement is a different characterization of the hardness of this problem.
You could instantiate your problem by just saying that the oracles are given by polynomial size quantum circles.
Yeah,
that's not what
with
you
the BQP-complete, we don't use oracles. Yeah, that's right. Yeah. Yeah, it's something like that. It's not. Yeah, it's there's no oracle in this BQP-complete.
Sorry, maybe the question. So to check again, the classical input right now is still like a quantum case. We query the IJ entry. I can read the IJ entries of the matrix. Or do we have some other type of I mean, input model, like the content is by the classical input model.
Yeah, we don't use that model. This quantum span model. Yeah, we don't consider that case. Yeah, that's true. Yeah, we don't use that model. Yeah, because something like the QRAM model is a little different than this model we used. Yeah, in the QRAM model, in the quantum span algorithm says, yeah, there is no exponential speed up for this matrix problems. So here
But the S to the square root of M, that's you're sort of tightly characterizing the quantum query complexity, I guess. What is the classical query complexity? Because you only state an upper bound. Like, is this S to the M minus 1 tight classically?
actually, I think we don't know if it's tight. We only have a lower bound, which is S/2, is square root of M divided by 6.
That's a lower bound for classical or quantum query?
Yeah, this is all classical results. Or maybe except the third one. Sorry, I shouldn't say that. Yeah, the lower bound is a classical lower bound. Classical algorithm, lower bound for classical algorithms.
And this S to the square root of M upper bound, is that a classical upper bound? Or
Yeah, that's the classical upper bound.
how do you do that? If I give you like a low degree approximating polynomial, how do you get a classical lower bound?
Yeah, we just use the first tree. We compute the ij's entry of a monomial first, and then just compute the linear combination of them, because the polynomial is a linear combination of monomials. And the first one tells you how to compute the ij's entry of a monomial. So for polynomials, you can just do the same thing. Just compute all the ij's entry of each monomial.
I'm confused again. So since you only care about query outline query diversity, then for sparse matrix, why can you just query everything then?
Yeah, you can query everything. In that case, the complexity may depend on the dimension. So you see, even if the exponential is to the m, this seems very large, but one m is not large, s is not large, it can be independent of the dimension. Yeah, all these results are classical results. So yeah, in the quantum case, we can just use the QSVT directly, and you can find a very efficient quantum algorithm computing this entry. And the complexity is linear in S and linear in the square root of M divided by some Pascal. So this is just you can just use QSVT directly to solve this problem. So if we look at this bound here, as you can see, just in terms of square root of M, you will see the quantum classical separation is exponential. On the lower bound, we have a lower bound of for quantum algorithms. It is a square root of n. So basically, from this point, you can see, it seems just in terms of the dependence on the degree, the quantum algorithm is already optimal.
For the practical case, the lower bound is for exact computing the M, the ij entry of A to the M.
No, the lower bound is you can, yeah, some errors are allowed. It's not exact computing the entry. Yeah, actually, when we prove the lower bound, we assume the epsilon is a constant. So you see, we don't have a dependence on epsilon. Okay, this is a result just for monomials. And we have general results for just a general f. Okay, we assume f is a continuous function. And A is sparse and Hermitian, and then computing the ij's entry up to some error epsilon. Then the complexity is summarized in this table. So in the quantum case, the complexity, the quantum algorithm is just using QSVT. It is SD divided by epsilon. Yeah, here D has a special meaning for function f. It is called the approximate degree. for in a bounded interval, -1, between -1 and 1, for a continuous function, you can always find the polynomials to approximate. And here, approximate degree means the degree is the minimum. So this is the degree D. And what we proved is a law bound in the quantum case. It is also at least linear in D. Yeah, classical. This classical algorithm is just as a most naive classical algorithm using the definition. But yeah, okay, maybe we don't care about that. What we care about is the law bound of classical algorithms. It is exponential in this D. Yeah, this is what we obtain. So if we just look at the approximate degree by comparing the up bound and the low bound of classical case, you will see there is the exponential separation. And in the quantum case, it is always linear in the degree D, so it seems optimal in terms of E. And this result is very similar to the polynomial method for Boolean functions. When we compute in a Boolean function, the polynomial method tells us the approximate degree is a low bound for computing Boolean function in the quantum case. And we obtain the same result for functions of matrices. But maybe something different is, for functions and matrices, it seems this approximate degree just characterizes the complexity. But for Boolean functions, approximate degree is just usually a low bound. There can be some separations between current complexity and the approximate degree. So this is our main results. So any questions about this table?
The classical lower bound is exponential in D. Is this for one particular choice of F, or does it hold for every F?
It is for all F. So F, it is for F. Yeah, that's true. It's seems quite surprising for us. And of course, this is the worst case complexity. It basically means for any F, you can always find a bad A, such that computing the IGS entry of FA is hard. It's as hard as it's kind of exponential. Okay, this is our results. So next, I will briefly introduce how we obtained this table. And actually, this is our main result. Actually, this is the most important result in our paper. It's okay. Let's see what it says. F is a continuous function between -1 and -1 to 1, and it has the odd part fx minus f minus x divided by 2. Then you can find a symmetric diagonal matrix. Okay, it has some properties such as that BI or BI are non-zero, and the operator of A is bounded by 1, and the one entry of FA is at least epsilon. And this epsilon is epsilon used in the approximate degree of F odd. Yeah, here one quite important thing is the dimension of this matrix is the approximate degree plus a constant here. Okay, this is I think this is the most important results used in our work, and all other the low bounds are based on this theorem. I think I will not talk about the proof of this theorem because it uses some techniques like linear semi-infinite programming and the dual polynomial method, and also combine some properties of diagonal matrices. Okay, so this is our key theorem, and we will use this key theorem many times in this talk. So, this is just for F odd. We have a similar result for F even. And you can see now F odd is just fx minus f minus x divided by 2. So approximate degree of the F odd is very close to the approximate degree of F.
So this matrix is supposed to be the bad matrix for a given F.
Yeah. I think once F is given, there is yeah, so there is a method to construct this matrix based on some results from linear semi-infinite programming. So yeah, this is quite important in this class. So any questions about this result?
So the operating norm of A being at most one
Yeah.
means that the BIs have absolute value at most one.
Yeah, that's right.
And then not sure how to interpret the one n correlate of A's at least epsilon.
Yeah, that's yeah. So this is maybe yeah. That's maybe something like I guess this is not because chart diagonal matrices is used in the random walks of a line. So yeah, yeah, yeah. I don't have a good intuition why it is at least F score.
Is it some kind of trade-off between the degree of this function and how far you have to walk on the line and how much weight you want to get at that furthest point?
Oh, wait, but yeah, for a moment I thought that if you square A, it becomes diagonal, but that's not the case because B1 and B2 are in the same column, right? So if you take higher powers, you do get non-zero values. Currently, the entries that are not filled in are all zero. Yes.
It's like a walk on the line with these weights given by the bees.
This matrix has only like 2 times degree many non-zero entries, right? So you can actually just using your sparse oracle recover the complete description. So how on earth can you get like s to the power degree is a lower bound on the query complexity?
S to the degree.
Yeah. Right, the degree is roughly n here.
Okay, maybe yeah, I will explain that. I think yeah, I will explain how we obtain this exponential.
Is it not right that there is an upper bound of 2 times approximate degree for the query complexity of this class?
Yeah, for this matrix, yeah, that's true.
But this is not the hard matrix that will
Because this is yeah, this is not the hardest matrix. We use this matrix to construct a new matrix. Yeah. So yeah, okay, yeah. Okay, so this is yeah, this is the most important result from this. Okay, maybe let's start from the quantum case, how we prove the law of one. And actually, this technique is already used in the non-fast convergence theorem. We try to reduce the function of matrices to this parity problem. So in the parity problem, we are given x1 and xn, they are 0 or 1, and we want to compute the sum of them, modulo 2. And it turns out quantization is also hard. And the quantum complexity is the order n. So this is a hard problem. So to build this connection to parity problem, we use this kind of graph. There is a weighted graph. The nodes, the vertices are I and B. Here, I is 0, 1, and n. So, and B just a bit, 0 or 1. And the connection, the edges between, is something like between B and B plus Xi. So, and the weights, okay, I guess this is the most important thing. You have to choose the weights very carefully to, to build the connection between functions and matrices and this parity problem. Okay, maybe before we say the weights, maybe we can see an example first. So there are just 2 levels of nodes. So in the first, the second coordinate is 0. In the top layer, okay. In the top layer, the second coordinate is 1, and the connection is totally determined by x. So x is x1 is 0, so it means the connection is between 0, 1, and 1, 1, and 0, 0, and 1, 0. But if and x2 is 1, so the connection is between the top left and the down the nodes in the there. Okay. So there is a cross in the second node. And the X3 is also 1, so there is a cross here. And the last X4 is 0, so it is just 2 horizontal edges. Yeah, this is the construction. Okay, then, okay, so just from this example, you can see this graph G is basically just 2 passes. So 0, 0, and 1x1, 2x1 plus x2, and then so on. And the sum of all xi, they are connected, they are in the same path. And the second path is 0, 1, and the last node is n1 plus x1 plus x2 plus xn. So essentially, G is just 2 passes. And if we set A as the adjacency matrix of this graph, so essentially, this because it's just 2 passes, so the adjacency matrix is just 2 symmetric diagonal matrices. And there are 2 cases. If the sum is 0, and you will see 0, 0, and n0 are in the same path, and 0, 1 and n1 in the same path. So 0, 0, and n1, they are in 2 different paths. So they are not connected to each other. This means FA, this entry of FA is always 0. And in the second case, suppose the sum is 1, then we want to find the appropriate weight such that this quantity is large, is far from 0. Yeah, far from 0. And because it's just a tridiagonal matrices. And yeah, this is how we obtain this weights from the key theorem, because in the key theorem tells us how to choose the weights, and this entry is large. So if you can compute this entry of FA, then you can distinguish which is the case. And so you can just solve the priority problem. So the priority problem is hard, so this problem is also hard. Yeah, and here it's quite important to make sure this the n is related to the approximate degree. Yeah, as I mentioned previously, this idea is inspired by the proof of the non-fast forwarding theorem. Okay, this is how we proved the quantum law bound is the approximate degree. Okay, so is this clear?
So again, what F you choose? What is F here? F could be anything here? Or?
Yeah, F is anything. I think the important thing is how we choose the weights. The F is fixed in this problem. So this result is for any F. And for any F, we can always find some weights such that this entry in 0, 0, and 1, this entry is larger than epsilon.
It could be that you have an F where the range of the function is like 0 to epsilon over 2, right? It's impossible to satisfy this. Yeah, so suppose there's no input for F where the value of F is bigger than epsilon. It's impossible to satisfy this.
Yeah, that's for any F. We want to find A such that it's large.
But if F's effective range is between 0 and epsilon over 2, then this is impossible to realize.
Okay, yeah, in that case, yeah, that's true. So
in that case, the epsilon approximate degree is actually 0 because you can just take a constant number.
So we assume F is between -1 to -1. We don't say it's very small F.
The -1 and the 1 are actually reached by some inputs.
So we don't think F is too small. Otherwise, yeah, it's. So this is how we obtain the quantum law bound. Actually, we use another problem. We try to reduce the problem to this correlation problem. And in this problem, we are given two Fourier functions, G1 and G2. And yeah, DI is just like a diagonal matrix in them, so something like the oracle. And A is a Harman matrix. And we care about this quantity here, phi G1 and G2. It is defined as the amplitude of L0. So it's the unitary in the middle is just a Hadamard to the nth tensor, D1 Hadamard, D2 and Hadamard. So this you see, just from the description of the unitary in the middle, you already have a quantum algorithm to compute this quantity. Yeah, the goal we try to approximate this quantity here. So this is a easy problem for quantum computers, and yeah, the important part is it is a hard problem for classical computers. And Ernst and Bennett proved that this classical law bound is 2 to the square root of 2 to the n divided by n. So we will use this result in the proof of a classical law bound. So to build the connection between this correlation with the function of matrices, function of sparse matrices, we use another trick called Feynman's clock construction. In Feynman's clock construction, for any unitary, U1, U2, and Un minus 1, you can define a Hermitian matrix such, yeah, it is generated by this U1, U2, and something, and UN minus 1, and with some, here, yeah, we added some B1, B2, some parameters here. But in Feynman's construction, there is no B1, B2, it's O1. And here we introduced some B1, B2 intentionally. And they are real numbers. So A is a Hermitian matrix. Okay, it looks like a random walk. So if we consider a subspace, this is psi t. The t is, we call it the clock. And inside t, it is something like the evolution of the first t unitaries. So ut, u, and u1 try to cat 0, the initial state. So in this subspace, A looks like a random walk. So in this subspace, the matrix of A is just a symmetric tridiagonal matrix, and the dimension is a capital N. So this is a Feynman's construction, clock construction we will use. Okay, so we will combine this construction with a correlation problem. And in the correlation problem, the unitary U is H tensor and D1 H Hadamard, D2 and Hadamard gain. Here the sparsity of A is totally determined by these unitaries. So if we want a sparse unitary, a sparse matrix, but H is not, Hadamard matrix is not sparse. So, but we can just decompose Hadamard into a product of several sparse unitaries. For example, this is the one way you can decompose. But of course, you can use like 2 Hadamards in the first factor. Okay, let's say we just use this kind of decomposition. So the matrix, the first matrix, Hadamard tensor identity, the sparsity is just 2, so it's a sparse matrix. So if U1, U2, and UN minus 1 are sparse, A is also sparse. Here we know D1 and D2 are sparse. So with this decomposition, every unitary in this U is a sparse. Now we have 3n plus 2 unitaries because each Hadamard decomposed into n terms, and there are D1 and D2. So there are in total 3n plus 2 unitaries. And we consider the initial state is 0, 0. And the last state, yeah, for this psi t, one t is n minus 1. So this un minus 1 and u1 apply to cat 0. So this is basically u. So So for phi and psi n minus one, it is just the first register is n minus one, and the second register is this unitary applied to K0. Okay, let's because we care about the functions matrices. Sorry, we want to compute entry of functional matrices. So let's consider another entry. This is phi n minus one. So on the left hand side is FA applied to psi zero, and phi n minus one. This is the entry of FA, and yeah, you just can compute it. Just use the definition. You can compute. It is the product of two terms. The first term is FA applied to psi zero and psi n minus one, and the second term is this quantity we used in the correlation problem.
What is the G1, G2? What is G1, G2?
Yeah, we want to build a connection between functions and matrices and the correlation problem. Yeah, this is how we want to use a correlation problem to prove a classical law bond.
G1, G2 are Boolean functions on the Boolean cube. The inputs to the correlation problem.
Actually, no, not Boolean. Boolean. It's
So the I was just GI, the values on the diagonal, the either 1 or -1. Right? I think that was the setup.
okay, in the correlation problem, this is a quantity we want to compute.
Yeah, so it's exactly what I said, right? G1,
And
G2.
the
are Boolean
correlation
functions.
problem, the construction, in this business construction, we want to use a matrix of this form. And this form is, this matrix, hopefully it has some connection to the correlation problem. And we want to use this matrix A to prove a classical law bound.
Yeah, I understood what G1, G2 is, so it's all good.
Okay, yeah. So we don't consider Boolean functions because what we care about is just a function of our matrices. It's this correlation problem is just a problem we want to use to prove a law bound. Yeah, this matrix A is what we want to use. And this U1, U2, and UN minus one, they come from this correlation problem. Yeah, we use this, and then you will say, you will see that this entry, this left-hand side is the entry of FA, and on the right-hand side, you will have the correlation problem. But the correlation problem is, we know a lower bound of this correlation problem. And but in the middle, the quantity in the middle, yeah, it is a quantity you can compute very easily because in this subspace, A is a small matrix, so you can compute FA this quantity very easily because dimension is small. And yeah, this is how we prove that computing this entry is hard. Yeah, of course, here I didn't compute the complexity explicitly. But this is the main idea how we obtain the law bound. Okay, so any questions about this?
So I guess what is important is that the small n and big N, they are both small, but then what is big is, I guess, this dimension of this register where the psi is. That's, I guess, 2 to the n.
Yeah, this, that's
The number of blocks here is small, but this block size is big.
Yeah, this matrix A can be very large because this unitary can be very, very large. So the matrix A is large, and in this subspace, A is a small matrix. Okay. So that's why we can say, okay, this is easy to do this in the middle. this is how we use the correlation program to obtain a law bound computing or entry of A. Okay, finally, we'll talk about something that is BQP-complete. There's a definition, BQP-complete is long, just maybe that's the original interface of the definition of BQP-complete. It is sometimes when I say BQP-complete, it is a promise problem. We have a set of promise problems, yes and no case. And we can say promise BQP, the set of the promise problems that can be solved by a uniform family of quantum circuits. This uniform family is okay. First, it is a polynomial sized quantum circuit, and second, we have efficient classical description of this quantum circuit. So for this circuit Y, when it is applied to a computational basis, you will produce a quantum state of this form. If X is in the real case, then you will accept with high probability. So the actually of 1 is large. If it is in the no case, then you have to reject it with high probability. So basically, this is the difference of these two actions. The probability is larger than, is greater than 1/3 or smaller than minus 1/3. Okay, this yeah, okay, maybe you already know I don't care about BQP-complete because it characterizes the hardness problems in BQP. And also it characterizes the power of computing because if you can prove, for example, BQP-complete is larger than P, then you will say the quantum computers can solve some problems that classical computers cannot efficiently solve. Yeah, so far we have many examples. Just for example, this computing into the RAT, this computing simulation problem, solving linear systems and the matrix powers, and also approximating matrix polynomial, they are all proved to be BQP-complete. And here we consider another problem. And we call it the entry estimation problem. So we have a bounded polynomial, continuous polynomial, or continuous function from -1 to -1, and A is n times n sparse permission matrix with bounded operation, and epsilon1, epsilon2 are some parameters in IJ are two indices. We assume one of the following holds. As the IJ's entry of FA is greater than epsilon1 or smaller than -epsilon2, and we want to decide which is the case. Yeah, this is a problem we want to consider. And the theorem says if the approximate degree is large enough, then this problem is BQP-complete. I guess maybe this is our surprising because that we don't we hope that when the approximate degree is large, yeah, maybe it's hard for classical computers. And actually, this is almost a corollary. Actually, the proof is already hiding in the proof of the classical law bounds. Because when we prove BQP-complete, a commonly used method is using Feynman's clock construction, and we already saw how we used this construction in the proof of the classical law bounds. So just to recall, we have some states: the initial state, the last state, and a state we care about. Yeah, here we consider another unitary. This is Y, or this Y is Y used is any promise BQP-complete problem. Of course, here what I mean is the second radius is cat 0, but we can just replace it with anything we care about. So we just use the cat x0, and you will see, just do the calculation, you will see, if x is yes, then this quantity is greater than epsilon divided by 3. If it is in the no case, then it is smaller than -1/3. So we have a separation in these two yes and no cases. Yeah, this is the whole proof. It's
So I'm still confused about the input model for the matrix. Right now, you are no longer have the query access to the matrix, right? So how can I access to the matrix? How do you give me the input?
you mean how to query this matrix.
No, I mean, like Ronald mentioned before, like you want to show this.
Yeah, here we don't have mode in our course to query the matrices. We want to, in this kind of proof, you need to say any any promised BQP complete problems can be reduced to this problem. Here we have, I guess the thing is, okay, what I want to say is, in this Y, we have, as we assume we have, we know it's, Y is a quantum scale. I think we assume we know it's a classical description of each gate in this Y. That's, yeah. So here, I guess this is the definition used. No, this Y is a uniform family of quantum circuits. And the uniform basically means, you have a efficient classical description of this circuit. Of course, it's a polynomial side because we hope it can be solved efficiently by a quantum computer.
I think the question is really like in the problem as stated on this slide, how is the input given? This slide, yes. No. Like, when I said this slide, that slide.
It's a slide.
Yes, yeah, exactly. How is the input given here?
Okay.
The little n is probably very big here, right?
Yeah, this is the dimension, yes.
This has nothing to do with the actual number of input bits to this problem. How is it given?
J inputs.
Yeah, IJ are inputs.
Okay, why does that have nothing to do?
The inputs, I mean, in my complexity theory, right? The input is an n-bit string. That's very standard. Here, the letter n means something very different. That's something much bigger than the number of input bits.
Right.
But my real question is like, how do you write down the classical inputs for this problem? Because it's also your next question.
Yeah. And it looks like they might give you like if I understand correctly, maybe the input is received as like a classical description, quantum circuit, such that they will make some certain, like start with Kij0, it will map to Kij Aij. Is this the input the way you give your input? You give me the classical description of a quantum circuit, which maps Kij0 to Aij. Is this the way you give us your input, or?
This will assume sparse. Yeah. Yeah, I think I need to double check this, but I guess if I remember correctly, maybe. Yeah, do we still need oracles to query this? Think about it. Once Y you have a, it's once we know it's been the description of this circuit, maybe we can know its entries in some way.
So one way to deal with the A would be to give small quantum circuits that compute the two oracles for you.
Yeah, since yeah, we assume Y has a decomposition of some quantum gates, and each gate you know you have a efficient.
Not the Y, right? Like in the problem that you're reducing to, like the earlier slide, there's an A there. The question is, how is that A
yes.
given?
Yeah, because
There's also a question, how is F given? Because F is a continuous function, like it might be very complicated. How is it given? To write out finite bit strings for the inputs.
should be given just directly, you know what is F, just an explicit formula for F. Like fx is just, for example, x to the dth power, something like this.
Yeah, and those are simple examples, right? But like your problem allows you to give any continuous function F as input.
Yeah, when we say this, F is given in advance, so you don't need to, say how F is. I guess here what I mean is that you know F explicitly, you know what is F.
Oh,
So are you saying that like you have a different problem for any F? So you have an F is given and you have like I don't know, this is like a family of BQP-complete problems. Do I think of it like that?
Yeah. For example, you just give it F. You know F. You should know F in first. For example, you could say Fx is just X inverse next to the dth power into the IST. This is something we know in advance. Then the point is given. Once that is part, I think it doesn't know everything about F.
there's continuously many continuous functions from -1 to 1.
Yeah, continuous just property of this function.
No, there's continuously many such functions, right? There's like uncountably many such functions.
Yeah, right. So you could take yeah, okay, anyway, you actually should be given in advance. Just when you pick a continuous function and you can pick a continuous function and if the approximate degree is large enough, then suddenly the problem is complete. Okay, anyway, I'll check how A is given. It should be given as a random outcome.
It could also be given as an approximating polynomial, at least that degree.
And fx.
Yeah, you could actually change the problem a little bit by replacing that F by the approximating polynomial. Should be easy to describe because you just give the coefficients of the monomials.
Okay, then this table is the results of the quantum classical law balance. Just like the point from the approximate degree, you will see quantum algorithm is indeed optimal, and the quantum classical separation is exponential. And we also have some BQP-complete results. And yeah, about our question is, yeah, actually, we didn't say anything about the dependency of Ashley. Usually, in the quantum case, so in the quantum case, to approximate something, maybe the technical we can use absolute estimate. We think the one-hour estimate should be a law bound. But yeah, we don't have a proof of this. And another thing is, if we can say something about the PCP. And in this paper by in Legault, they also studied something about Pascal algorithms of computing functions on matrices, and they obtained some interesting results. Yeah, I think there are some connection between our paper and this paper, and maybe, in this paper, we studied something about related to quantum TCP. So hopefully, there are some connection to the TCP problem. Yeah, thanks very much for your time.